Thank you. Welcome to everyone. So today what we are going to see, it is connected with testing of hypothesis in statistics. Initially we will introduce certain concepts related to testing of hypothesis. Then we will start doing problems taken from the previous year question papers. So that this is the plan. So to begin with, let me explain what testing of hypothesis is about quickly. So testing of hypothesis. Okay, so first of all, we should know what a hypothesis. Okay, in general, a hypothesis is a statement definition, and it says nothing about the structure. Okay, it's a general statement about anything which needs to be proved or disproved. Okay, but as far as statistics is concerned, such generality will not work. We should be very specific in what we are doing. Okay, we have to develop a testing procedure, okay, with some error structure, and we have to finally make some conclusion within the error bounds. So this hypothesis, okay, this hypothesis here is restrictive in nature as far as statistics is concerned. Okay, statistics is concerned. So here what we mean by an hypothesis is we will begin with a random variable, okay, x, whose distribution is known, okay, whose distribution is denoted by f theta, okay, and here what we assume is form of the distribution is known, form of the distribution is known, but value of theta, which is the parameter, this is unknown. This is how we start with. So we want to test some statement about this theta. We want to test some statement about this theta. Particularly, it can be something. So the one that we want to begin with, okay, that is called null hypothesis. And the null hypothesis, definition of null hypothesis varies with different authors. Okay, the one that is supposed to be rejected, that is a famous definition. But in general, we can assume that it is the hypothesis about theta about a particular value, on a particular value. Okay, so null hypothesis is denoted by h naught. Say something like theta equal to 52. You can assume that this random variable x is age. This random variable x is age, and the distribution, okay, distribution is something like normal, because we know the form, and in normal also we will assume that usually the normal distribution has got two parameters. We don't know what about mu, but we will fix sigma square is equal to 10. Okay, sigma square variance we will fix it. Okay, so here this is the unknown parameter. So this is my theta. Okay, so theta equal to 52 in this sense means I am testing that the average age of this particular group or population. Okay, and by population here I don't mean always a group of people, okay, of a particular area, something of the sort. It is a collection of objects, that's all. It can be even collection of say non-living things also. It can be, suppose if I am going to take a sample of say 10 units from the production process of a particular product, my all production units in that particular group forms my population. Therefore, it is a universal notation that we use, say something like population, but it actually means it includes a general master set. Okay, that is the idea. So I want to test the mean of the population is equal to 52 years. I want to test this. And this the test of 52 may arise due to various reasons. Okay, it may be due to various reasons depending upon the situation. Say for example, 50 may be the cutoff value, and I want to test whether the average age is above 50. So I have safely taken it as something like 52. That may be one reason. If it is say something like senior citizen, it may be 65. It may be 65. I want to verify whether the group belongs to the senior citizen. Okay, then in this case I will be testing for 65 or something. And what about alternate hypothesis? Alternate hypothesis is one that negates your null hypothesis. Okay, alternate or alternative hypothesis. Usually it is denoted by H1, and in some books it is also denoted by HA. Okay, it depends. But majority notation is H0, H1. And the alternate hypothesis is that this is not equal to 52. This is not equal to 52. In one case, it may be not equal to 52. In one case, it may be, I may test whether it is greater than 52. In some other case, we may go for less than 52 also, depending on the situation. Okay, but my null hypothesis is this. Okay, my null hypothesis is this, and alternate hypothesis, depending upon the situation, it may vary. Depending upon the situation, it may vary. Say, for example, if I am testing the effect of a drug in reducing the weight, okay, in that case, I want to check whether the weight has got reduced sufficiently. So in that case, reduced thing that is less than 52 is my alternate hypothesis. Okay, and similarly, if I am giving a drug and after some time I want to see whether the number of platelets in the blood cells has increased because of my drug, because I want to increase the number of platelets. So in that case, I want to test whether it remains same at 52, the previous mark, or whether it has increased considerably. In that case, it is greater than 52. And in some cases, we are interested in testing not equal to, in the sense that even a thing which is less or above is not going to work for me, something of that sort. If I am producing a bolt for a nut, okay, and the diameter should exactly fit in. If the diameter of the bolt is less, okay, it will not fit in. Similarly, if it is more also, it is not going to be useful. So in that case, if it is not equal to, okay, then probably it will be a waste product. So in that case, I want to test whether it is a correct product, good product, or a defective one. So even more or less, anything is not going to be useful. Of course, we should here make clear the point that, so if it is not equal to means it is not exactly, it's not equal to. It can allow some variation, and that variation should be within the sampling error structure. Okay, this is one thing that we want to say. And when we prove this, okay, to prove or disprove, what we normally do is we will take a sample x1, x2, etc. from this particular distribution. Okay, normally proving or disproving requires some evidence. That evidence is collected from a sample x1, x2, etc., xn from the distribution for which we are testing. Okay, that is f theta. It in our case we can assume that it is normal, or in some other case it can be exponential, binomial, Poisson, anything, right? So generally I am talking about. And what about this x1, x2, xn? This is only a sample. That means we have a population, okay? We have a population which is bigger in size. This is my population. And now I have a sample which is very relatively small, okay? I have a sample which is relatively small. That is the idea, right? So this is my population, okay? This is my population, and this is my sample. This is my sample. Since we are trying to generalize certain things for the entire population based on the sample, we are bound to make some mistakes, okay? Because sample being part of the entire thing cannot replace the totality. So it is bound to have some error. So in testing process, we cannot be totally free from error, but all that we want is that error should be kept under control. So what are all the types of error that can get into the testing process? See, we may reject your null hypothesis when it is true. This is one type of error. Okay, this is one type of error called type 1 error. Type 1 error. Similarly, do not reject H0. Okay, do not reject H0. When do not reject H0 means you cannot say accepting H1. Okay, it is same as sorry, this is H0 when H0 is true. Sorry, then only it will become error. When H0 is true, and if you are rejecting it, it is called type 1 error. And do not reject H0. That means you accept H0, but strictly speaking, accept is not the terminology to be used for simple comparison, or in simple language I am putting it. Otherwise, I should not use the language accepting H0. It is not rejecting. Okay, whether it is rejecting or not rejecting. So the grammatical opposite will not come into play here. So do not reject H0 when H1 is true. This is another type of error. This is called a type 2 error. Okay. So it is always there at logarithms. Okay. When we try to, in a testing process, when we try to decrease type 1 error, type 2 error will increase, and vice versa. So it is something like this. So I will split the board. Okay, so it is something of this sort. I'll put it like it. 1 minute. That is, we may have two scenarios, right? This is your actual, okay, ACT. This is your testing result, okay. Actually, H0 may be true, or actually H1 may be true. Your test result will say H0 is true, or H1 is true, okay. So here, see what happens. Test, okay. Reject H0. That means H1, okay. When H0 is true. Okay, when H0 is true. So reject test is this, reject H0. That means you will say H1 when this is called your type 1 error. Similarly, this is called your type 2 error. When H0 is actually true, and your test is also saying that it is H0, this is a correct decision. Similarly, this is also a correct decision. So as I said, the type 1 error and type 2 error, okay, type 1 and type 2 errors, okay, they go in opposite direction. As one increases, other decreases. When you try to decrease one, naturally being error, we want to minimize it. But when the process of minimizing type 1 error, we will increase type 2 error. Okay, that is the natural link between the two. So what happens is we will see which type of error is more serious. Okay, which type of error is more dangerous. Okay, so in that case, we will fix type 1 error as more dangerous, and we will fix this type 1 error at alpha, normally usually at 0.05 or 5% level, or 0.01 at 1% level, and we will try to minimize this. Fixing this, okay, now it is a problem of minimizing the other one. Okay, test which for a fixed level of alpha, the one that decreases the type 2 error is called minimizes the type 2 error called is best test. Okay, best test, and when it works well for all the things, it is said to be uniformly most powerful test, UMP, uniformly most powerful test. Okay, we will do a problem under that, so there we will be seeing this thing in a little bit detail. Okay, fine. So now this is the idea. So when you fix alpha is equal to something like 5% and 1% and try to minimize the type 2 error, this is the testing procedure. Okay, and why we see these kind of things also naturally occurs in day-to-day life. Okay, so in judiciary also it is something like a testing process. Based on the evidence, the judge will pronounce a particular candidate is a say whether he has done some mistake or not. Okay, whether he is deserving punishment or not. So the same thing will happen. In reality, he may be a good person. In reality, he may be a accused. Okay, and similarly, the judge may conclude he is good or he is accused. Okay, so all the combinations may happen. But see, judging a person as accused when he is not accused, okay, that is going to be more serious rather than saying that non-accused, judge saying non-accused as an accused person. Okay, this is normally we used to say, see, it is always we can let 1,000 accused let go. Okay, but we should not punish one innocent person. So this is also something like a type 1, type 2 error balancing. Okay, so which one you can, which one is more dangerous and which one you want to fix. Okay, now I think we will get into the problem directly. So this is our problem, and this problem is taken from the year. Let me check. Yes, it is 2019, paper 1. So this problem is taken from 2019, paper 1, 2C. Paper 1, 2C. Okay. So what we have is, we have a distribution which is given as fx theta, fx theta or fx comma theta, both first. So the distribution is 1 by theta e power minus x by theta, 0 less than x less than infinity, in this range, 0 otherwise. Okay, so this is a positive value random variable because it takes positive values. And what is that they are saying? They are interested in testing the null hypothesis h naught theta equal to 2 against versus the alternate hypothesis h1 theta equal to 4. This is what they are giving. Now what about the samples? They say that x1, x2 or a random sample of size 2. They are taking two samples. One is x1 and one is x2. This is a random sample of size 2. Okay. So now what they have given is they have also given the test procedure. Okay. They have also given the test procedure. Okay. Let me continue this line and. Okay. So the test procedure says that you reject the null hypothesis when x1 plus x2 is from minus 9.5 to infinity. So this part. Okay. So I will take it separately. So the test procedure says it is all collection of all x1, x2 satisfying this condition. Satisfying this condition. That is, it is all x1 and x2 whenever x1 plus x2 is above 9.5, okay, below infinity always it will be, okay. So the lower bound is more important. So when the sum of the 2 points is greater than or equal to 9.5, you reject the hypothesis. This is your test. So this is your distribution. This is your known structure. But what we do not know is the value of theta, and that theta is tested for 2 against the value 4, okay, and they have given the procedure, and which says that when you take 2 random samples from the distribution and add, when the sum is greater than 9.5, then you reject the null hypothesis. This is all it's said. Now we want 2 things. One is the size of the test, and another one is the power of the test, okay. It is type 1 error, type 2 error. Type 1 error and 1 minus type 2 error is the power. Okay, first let me fix what about type 1 error, or say size of the test. Okay, they want 2 things. If you carefully see here, one is size, another one is power. We will take one at a time. Okay, and what is size? Size is nothing but, in this case, because we have single value in the null hypothesis and single value in the alternate hypothesis. Otherwise, even the size will have some. It will involve some concept of minimum and maximum, or infimum or supremum. Okay, so size here is reject h naught. Okay, when h1 h naught is 2. So this is your size. Reject h naught when h naught is 2. This is your size. Okay. Now we have 2 problems here. One is the problem associated with the concept of testing. Another one is the problem associated with the integration, right? Integration, or so to say, the problem associated with the distribution of x1 plus x2, the distribution of x1 plus x2. So we should be very careful which way you are supposed to proceed. Okay, so let me see probability of rejecting h naught. When I will reject, as I said, x1 plus x2 is greater than or equal to 9.5, I will reject. Under h naught, what is my theta? Theta equal to 2. Okay, so now what I want is, I want to find the distribution of x1 plus x2 under theta equal to 2. Okay, I know that x1 comma x2 are random samples, thereby they become independent, but I want to find the distribution of the sum total. Okay, once if I know the distribution, I can find this probability. So now the problem is shifted from testing to finding the distribution. Okay, so to some extent we have in our previous class we have found how to transform the variables and get the distribution. Okay, but here if you carefully see in the previous class, when we use the technique of Jacobian to transform, okay, so we had a similar structure, x1 plus x2. So you can use some dummy transformation, x1 minus x2, and you can get something like y1 and y2. That is possible, but the problem here is x1 plus x2 is positive because x1 x2 are positive. But if you introduce x1 minus x2 as a dummy transformation, this will become negative, because sum of 2 positive is always positive. Difference of 2 positive need not be positive. Okay, 2 minus 4. Both are positive, but the difference is negative. So these kind of the transformation technique that we used in our previous class, that will not work here. So what we will do is, we will adopt for a different technique. Okay, so what we will do is, we will find the distribution function of x1 plus x2. Based on the distribution function, okay, once we find it, we will differentiate that function, we will get the density, and we will use that density to get the size. Okay, so now let me start with the distribution function, x1 plus x2. I will call this as y. Okay, y is equal to x1 plus x2, and this is less than or equal to small y. This is what I want. See, in the integral symbol, we should see how in the 2 dimension this works. Okay, how the 2 dimension this works. Okay, because it is a 2-dimensional random variable, we should little bit be careful. So okay, So this is my x-axis and this is my y-axis, and this axis is this value, okay, and this value is x is equal to y. This line is x is equal to x1 equal to x2 in this case. So I will fix the values. This is x1 axis because we have x1 plus x2. This is my x2 axis, and this line is nothing but x1 equal to x2, and all the points, but I want x1 plus x2, so I should not use this. One sec. So x1 plus x2 equal to y. Okay. The line will be something like this. It's a downward sloping line. Okay, this is my x1 plus x2. Okay, I will put it here. So this is my x1 axis, this is my x2 axis. Okay, and this is my y. This is actually y comma 0, and this is 0 comma y, so that all the points in between you will have. So this line is x1 plus x2, sorry, this line is x1 plus x2 equal to y. All points below this, okay, is that what we are interested in, less than or equal to y. Okay, so I am going to express this in the double integral. Okay, and this value is equal to inner integral. Okay, in the outer integral 0 to x1. Okay, so x1 is going to vary from 0 to y. This is with respect to dx1. In the inner integral, okay, this is the base. I am moving vertically. It is 0 to, I want x2, which is y minus x1. This is y minus x1. And what about the density? So we have actually f of x1, x2. So this is the this is with respect to dx2. The outer integral is with respect to dx1. So this is the integral that I am supposed to evaluate. This is the integral. Okay, this is my integral I want to evaluate. Okay. So I think I will move to the next board by taking these values. So better. So any questions so far? If you have any questions?
No, sir.
Okay, fine. So in that case, I will move to the next board. So this part we require from the previous thing. I have taken it from there. Okay, of course, we need the density also. One sec. Let me save this. Okay. Fine. So now we will start integrating the things, which is equal to integral 0 to y and integral 0 to y minus x1. In mathematical sense, this is also known as convolution. Okay. In fact, we can extend this for summation of 3 also, then it will become triple integral. Okay, so the idea is same. So you can extend this as a n-fold convolution for sum of any general n variables. Okay, so and what about f of x1, x2 being random samples? They are independent. So joint density can be broken into marginal density. So f of x1 into f of x2. So it will become theta e power minus x1 by theta, again theta e power minus x2 by theta dx2 dx. Order of integration is more important because it is not a rectangle, so that we can move it in any direction. First we have to integrate with respect to x2 and then we have to integrate with respect to x1. So first x2, outer integral is x1. So this is equal to, so we can use simple integration techniques that we have. Okay, 0 to y. 1 theta, here we have 1 theta, here we have 1 theta, that can be taken out, 1 by theta square. Okay, so and when we integrate with respect to x2, x1 is constant, so e power minus x1 by theta, we can take it out. And we have integral 0 to y minus x1, okay, y minus x1, e power minus x2 by theta dx2. Okay, the outer integral is dx1, which is equal to 1 by theta square integral 0 to y e power minus x1 by theta. So this we can integrate. This is something like integral e power ax. Okay, this resembles something like integral a to b e power ax. So e power ax means it is something like e power ax by a. Same logic. So dx we have taken it out. Okay, so this is e power minus x2 by theta divided by minus 1 by theta. And what about the interval? Interval is from 0 to y minus x1. Outer you have x1 dx1, which is equal to 1 by theta square integral 0 to y e power minus x1 by theta. And see here what happens. Here this theta will come to the numerator, so I will bring this theta. Okay, and we have a minus sign that I will exchange with the upper and lower limit. Okay, so what we have now is e power minus x2 by theta, upper limit 0, lower limit y minus x1. Because of the minus sign, I am interchanging the limits dx1. This is equal to, now it is 1 by theta, because 1 theta will get cancelled, 0 to y, we have x1 by theta, and here if you substitute x2 0, e power 0 becomes 1, minus, if I substitute y minus x1, it is e power minus, okay, y minus x1 divided by theta dx1. So which is equal to, so it is since I am parallelly explaining and going, it takes time. If you are comfortable with integration, you can quickly do it. Okay, it's not going to take that much time. You can rush through like anything. Okay, so now we have integral 0 to y, and I want to this multiplied by this. I will have minus x1 by theta. If I multiply this by this, power will get added, minus x1 by theta. Here what will happen? Minus y by theta, minus into minus plus x1 by theta. For the entire thing, okay, we have to integrate with respect to x1, which is the outer form. 1 by theta 0 to y e power minus x1 by theta minus, see here these two things get cancelled. Okay, minus x1 by theta plus x1 by theta, they get cancelled. So what happens is what we are left with is minus e power minus y by theta, and we want to integrate this with respect to dx1, which is equal to 1 by theta. So when I integrate this, what will happen? Integrating this with respect to x1, that is most important. So that will have something like e power minus x1 by theta, again minus 1 by theta. Okay, so this is one part, minus. See, this is not same as the previous one. The previous one has x1 in its terms, whereas here there is no x1. Having y is not connected with x1. As far as integration with respect to x1, y is a constant. So it is something like k. Okay, so if you have integral k dx, it is simply kx. So e power minus y by theta into x1. Okay, after being integrated, okay, we can substitute the limits from 0 to y. Okay, that's all. Okay, so we want to simplify this. After we should substitute the limits and other things. To some extent, we can simplify here, and I will go to the top of the board. Okay, so here what happens is 1 by theta. This theta is going to be the it is going to be taken to the upper end with minus sign. So minus theta e power minus x1 by theta. Okay, here minus x1 into e power minus y by theta 0 to y. Okay, so what I will do is I will copy paste this to the top. Okay, so that I need not repeatedly come back and refer. Okay, so I will also split the board. One sec. Okay. Let me paste what I have taken there. So this is what we had it at the bottom. So we will continue this. So it is equal to, so this is equal to 1 by theta. And see, in the upper limit, I want to substitute, so this is taken somewhere. Okay, you ignore this. 0 to y is the limit. In the process of copy paste, we have certain unnecessary things here. That's all. Okay, so this is 1 by theta. In the upper limit, I have to substitute y for x1. Lower limit, I have to substitute 0 for x1. Okay, so I will put it like this. Okay, there is a minus sign common to both, so I can bring that minus sign outside. So it is minus 1. Now it is theta plus the x1. Okay, so I will substitute the upper limit. Theta e power minus y by theta, because I am to substitute y for x1, minus for y, for x1 I have to substitute y. Now it is plus because I have taken the minus sign. Y e power minus y by theta. This is the upper limit. Minus lower limit. I want to substitute x1, 0. So e power 0 is 1. So it will become theta. Okay. And when I substitute 0 for x1, this will become 0. Okay, this will become 0. So my value now reduces to, okay, minus 1 by theta. Here what we have is theta multiplied by, okay, one second. This is my, let me be very careful. So, okay. So in the upper limit, we have theta. Here we are substituting y. Okay, here also we are substituting y. Lower limit, when we substitute y here, so 0 here, I am getting theta. And okay, this is fine. So I have theta e power minus y by theta plus y e power minus y by theta, and then we have a minus theta. So I have not taken common, that is one particular thing. Okay, let me check once again. So we have this minus, okay, fine. And the other one is plus. So this integration okay. So theta e power minus y by theta is there, and then okay. So because that 1 by theta we have left it outside. We have left it outside. So that is what we are supposed to substitute. Okay, and this is equal to. Okay. Okay, I will. Because we have 1 minus 1 theta outside, we can adjust this. Okay, that is one possibility. And here we have the theta, if you bring into the other side, okay, that is also a possible. So I will put it directly. So I will substitute it directly. 1 by theta. Okay, 1 by theta. We have minus, I am taking this theta with the integral value, right? Minus y by theta. Okay, this minus y by theta, And since we are taking the value inside, I will also supposed to have that 1 by theta. So this is because we have so I will tell where I have gone wrong. There is a small mistake here that we want to adjust. See, in the first case, we are supposed to take this value. This is fine. This is okay. But in the second case, okay, when we replace it, this is what we have actually. Okay, so I will put it like this. Because of the substitution, we have this problem. Okay, one sec. So I will take it directly from here. So initially we integrated this. As far as this is okay. And after substitution, this theta is going to the numerator, and we have this. This is only the limits. Okay, after limit. Okay, after substituting the limit. Okay, so this is something like outer limit that we have. Okay, so after substituting the limit, I will paste the things. Okay. That is a confusion. I have done it twice. That was the problem. So I will make it now. So now I will directly substitute. So what I have done actually is I have substituted the original value, okay, in the integration, okay, and instead of actual substitution, I went for one more substitution. So that is the place where I went wrong. Okay, so now I can directly put this integration. Okay, so what we have is one sec. The last, I will remove only the last part, not anything. So only this part. Okay, so because even that part we can retain, but I will tell why. Okay, the sign that we have taken outside, that is that will create some problem. Okay, now what is your left hand side? It is nothing but probability y less than or equal to y. What is your right hand side? I will take this minus inside, nothing else. Okay, so that will become when I take this minus inside, okay, this will become plus 1, okay, minus theta e power minus y by theta, and then this will also become minus y e power minus y by theta. So this is going to be my term, okay, which is my capital F of y. So I want the density small f of y. So differentiate the above with respect to y. Differentiation of this with respect to y, theta is constant. Okay, I can keep it as such. Okay, 1 is a constant, that becomes 0 minus theta. I am going to differentiate with respect to y. E power minus y by theta. For y, I will get 1 by theta, right? And this is to be done with product rule. So minus I have to take outside. First function, differentiation of second function. Okay, with minus 1 by theta, plus second function, differentiation of first function with respect to y, which is plus theta. Okay, so this is what we have. So let me simplify this. 1 by theta. Okay, here what we have is this theta will get cancelled with this theta, minus into minus plus. So I have e power minus y by theta, the first term. The second term will, okay, what will happen is it will become minus. It will become minus. Okay, minus y by theta. This and this they will get together, and there is a minus sign here. There is a minus sign here. It will become plus y by theta. Okay, e power minus y by theta, and this is a minus. This is a plus. So it will become minus e power y by theta. So now you can carefully see that we can, this is plus e power minus y by theta, this is minus. So these two things can be dropped, finally leading to fy of y. My density is, this is 1 theta, this is 1 theta. So 1 by theta square y e power minus y by theta. And what about the range? Since x1, x2 positive, x1 plus x2 is also positive. So this is greater than 0. Or greater than 0, less than infinity, 0 otherwise. That is how we have. So this is our density. Okay. One sec. And let me extend this line and come. Okay. So once this density is derived, okay, once this density is derived, this is what I am interested in. Okay, x1 plus x2 by 2. Okay, I think now I can find the size and power of the test. Okay, so it is little bit lengthy. Okay, so I have taken a problem that accommodates all the distributions, integrals, statistical hypothesis testing concept, everything. Okay, so we should be a little bit careful here. So what we have is now I should get the size of the test. Okay, first size of the test. And my size is nothing but, as we have already mentioned, this is nothing but probability, okay, x1 plus x2 greater than or equal to 9.5. Less than infinity is okay, that is accepted, which is equal to integral. So x1 plus 2 we have already written. So 9.5 to infinity. What about the density? It is 1 by theta square. I will take that outside. Y e power minus y by theta dx dy. Okay, dy. So I will slightly adjust this. I will leave 1 by theta. 1 theta I will get inside. Okay, 9.5 to infinity. And that theta I will write something like y by theta here. And e power minus y by theta dy. Okay, so now I will put y by theta as t. Okay, y by theta as t. So that will give me dy by theta equal to dt. So how this integral will now change? Okay, this 1 by theta dy is going to be my dt. Okay, I will put it here. And y by theta is now t and e power minus t. When y is equal to 9.5, t is equal to 9.5 by theta. 9.5 by theta up to infinity. But under null hypothesis, what is your theta? Theta is going to be your, the value of theta is 2. So this is 9.5 by 2. Okay, 9.5 by 2 value is, we have 4.75. This 4.75 to infinity. T e power minus t dt. So this is the integral that we are interested in. Okay, this is the integral. So that is you can integrate with the UDV technique. Okay, that I will do it in the next board. I will take this to the next integral or next board. Okay. So since I am going to move to the next board, if there is any question here, let me answer. Otherwise, I will go to the next board. Yes. Any question?
No, sir.
Okay, so I will go to the new board. So I will place this. This is the integral that I have. Okay, so let me quickly integrate this using the UDV principle. So integral 4.75 to infinity. I will make this as your u and this as your dv. So e power minus t. Since it is a minus, I will put like this, which is normally written as uv minus u1 u dash v1 plus u double dash v2, where u dash u double dash consecutive differentiations, and then v1 v2 they are consecutive integrations. Okay, this is equal to, so in our case it is t is u and then minus e power minus t is v minus, when you differentiate t we will get this. When you integrate this, you will get e power minus t. One minus will come, that will offset the minus one. The next term will vanish because if I differentiate one, it is 0. Okay, and this value over 4.75 and infinity. Okay, which is equal to. So we can substitute this. Okay, which is something like there is a minus sign common present in both. I can take that minus sign outside and interchange the limits. So I have t e power minus t plus e power minus t under the limits 4.5 to infinity, which is equal to, say we can take out e power minus t outside. So t plus 1, okay, which is 4.5 to infinity. This is a simple substitution. Okay, this gives me something like minus infinity. Okay, at upper limit it is 0, right? E power minus infinity. Lower limit minus of this value that we have. Okay, that value is we have, you'll put it directly 5 point, if it is 4 point plus 5 point, this is not 4.5, 4.75, right? 5.75 into e power minus 4.75. This is what we have. And as we have moved out, okay, the sign here itself we should interchange. Otherwise, I should put a minus sign here. One of the two things. So this you can use the calculator and you can get the value, right? And this is this value is 0.049747. This is a simple calculation that you can verify at later stages. Okay, this is my size. Okay, this is my size, and now I want to get the power. So to get the power, what I will do is this is going to be slightly adjusted. Okay, so I will put it that way, so we will not waste our time. Okay, so what I will do is I will copy this and I will paste this, okay, separately here, and let me see what are all the adjustments we want, because we define power as similar way with some difference. Okay, what is the power? Previously we have defined what is size. Power is 1 minus type 2 error. Okay, power is, I will put it like this, 1 minus probability of type 2 error, which is equal to 1 minus type 2 error is, first one is rejecting, this is not rejecting H0 when H1 is 2. Not rejecting when H1 is 2, which is equal to 1 minus not rejecting H0. Okay, so so what I can do is I can if it is not rejecting H0, it is see, when it is greater than or equal to 0.9.5, it is rejection. Okay, but we want this no rejection. No rejection means it should be less than, so it should be 0 to 9.5. Okay, this is the rejection region. And what about this area? This area is the same as the one that we have there. Okay, the area is something like t e power minus t. Okay, t e power minus t dt. So that is what I am interested in. Okay, that is what. And what about theta in this case? So you should also be very careful with respect to this. Is only after we get this theta, dy, after substitution only we have this. So previously it was theta, which is 2. So we have this 4.75, which is nothing but your 9 by 2. Now it is theta is 4. Okay. Now under H1, because this H1 theta is equal to 4. So now we have 9 by 4, which is equivalent to 2.375. Okay, this value is 2.375. So now we have something like instead of integrating with respect to 0 to some upper limit, okay, 0 to upper limit, that upper limit will get changed now. So instead of this, now we will have something like 2.375. 2.375. So this is a simple integration that we can integrate separately. That is what I am planning. So I will put it, I will integrate this separately here. Okay, I will take this down. So I will paste it here and use both the sides. So I will split the board horizontally now. That is more convenient to me. So now I will split the board like this. Okay. So now let us see what happens. This is equal to 1 minus 0 to 2.375. Okay. So that value already we have. Okay. 0 to 7.5. That integration is probably, so already we fixed it to be t e power minus dt. Same thing only. T e power minus t dt. t e power minus t dt. So I can integrate this first and then subtract it from 1. Okay, that is it's not a big thing. So I will consider this integral 0 to 2.375, and this is my u, this is my v. As in the previous case, I can use the same thing. Okay, I can use the same thing. So this is equal to uv, that is my t minus e power minus t minus t is 1. This will become e power minus t, and this value is 0 to 2.375, which is equal to both terms have minus sign. I will take out even e power t, I will take out. Then I will get t plus 1. Since both the terms are positive, negative, I will interchange. It is 0, 2.375, which is equal to, you can substitute for the upper limit. So this will become 1. Okay, this is 0. The entire thing becomes 1 minus. And what about this? This will give you something like e power 2.375, and this is multiplied by 3.375. Okay, that's it, that you can use the calculator, and let me get the value. It is exp minus 2.375. So that value is minus 0.09 minus 0.09301. So it is, one sec. Here we have left out that minus sign. Okay. So because e power is always plus, 0.093, 0.09. Okay, I will copy paste this better. So this is one value that we have, e power, and then this has to be multiplied by 3.375, which is equal to 1 minus that value into 3.375. 3.375 multiplied by this value, and the new value is this one. Okay, so I will, okay. Okay, now I will resubstitute everything in the original. So what I have now is, already I have some 1 minus, okay, so which is equal to, so now I have 1 minus the value that I evaluated. Okay, the value that I evaluated is 1 minus 0.31 something. Okay, 3139. Okay, whatever may be the thing. So ultimately 1 and 1 will get cancelled. We will get 3139. So this is my power. Okay, this is my power. So see, we should be very careful in doing such problems, because see, you can we have done so much of integration, and we should be very careful about the things. Otherwise, it will be a little bit difficult. Okay, now I think if there is any question, I am ready to answer. Otherwise, I will move to the next problem. Yes?
No question, sir.
No question. Fine. So then I will move to the next problem. Okay, I will. The problem can be done quickly. So I will copy paste this problem. Okay. So this is our problem which okay, now you can clearly consider a random variable x with PMF, probability, mass function, and your theta takes two values, 1 by 2, 3 by 4. Okay, and x takes six values, 0 to 5. And for different combinations of x and theta, okay, they have given the density values or mass values, right? Say, for example, if x is 2, if x is 2, and theta is 3 by 4, this is going to be my value. Okay, so we have a density which varies with respect to x comma theta, and x we know can take value 0, 1, 2 up to 5, and theta takes only two values, 1 by 2, 3 by 4. Okay, and finally we can see what is the mass function. Now what we are asked is for obtain the best critical region. Okay, best critical region to test the null hypothesis. H naught theta is equal to 1 by 2 against theta h1 theta is equal to 3 by 4. This is what we are supposed to find. Okay, now it is given that the alpha is 6 by 32. That is what the crucial thing lies. It is given that alpha equal to 6 by 32. Now we want to get a test. Okay, so we should say, as in the previous problems, greater than something or less than something or different combinations. See here under the null hypothesis is alpha equal to 1 by 2. I have only two combinations leading to 6 by 32. Either it should be 0, 1 or it should be 4, 5. One of the two things. My critical regions, my critical region 1 is, it should be something like x is less than or equal to 1. That means 0, 1. Okay, that is x is equal to 0, 1. This will have an alpha value of 6 by 32, 5 by 1 by 32, 5 by 32, 1 by 32, 5. And there is another region, critical region for the same thing. X should be greater than or equal to 4. That means here x is equal to 4 or x is equal to 5. This case also we have 6 by 32. 6 by 32. Okay, this is 32. Now both the values have the same size. So, but what it is said is we should have the best critical region. Okay, it is said that we should have the best critical region. That means among these two regions, which has got the maximum power. Okay, so now let us see what about the power of region 1. Power of region 1. So that means under alternate hypothesis, what is the probability? Okay, under alternate hypothesis, this is say 1 by 1024 plus 15 by 1024, which is equal to 16 by 1024. This is power of region 1. Similarly, power of region 2, see we said it is 4, 5. For 4, 5, you can see from the table 4, 5. So you can see it is 405, 243. 405, 243, 1024, which is equal to 648. 648, 1024. So now you can clearly see which one is better. So though both the things have alpha 6 by 32, power changes for the two regions. Okay, so what is our best critical region? For the same alpha, we should get maximum power. That means our critical region 2 is going to be the best critical region. So we should, the answer should be, what is the best critical region? So best critical region is, okay, set of all x such that x should be greater than or equal to 4. That's all. This is so when you know the concept of power and thing, we can derive, because here there is no integration process involved. It is given in the table, so concept is more involved. In the previous problem, integration requires more time, so you should be very careful. We should be very careful. So I will do one more problem of simple nature and complete this. So let me see. Any question from here? Okay.
No, sir.
Okay, fine. I will go to the next problem. Okay. So my next problem here is again it involves estimation. Okay, so I will paste the problem first. Okay, this is my problem. Okay, so and it is taken from 2016 1D. So the paper is 2000 from 2016, paper 1D. Okay, so we are given a PMF. Okay, in which as in the previous case we have different combinations. As in the previous case we have different combinations. Wherever in which we have x is equal to x can take value 2, 3, and 4. X can take value 2, 3, 4. And what about the value of your p or theta? Theta can take value 3 values, 1 by 4, 1 by 2, or 1 by 3 by 4, 3 values. And for different combination, what about the values? That is given in the table. When x is equal to 3, I will round it in different color. When x is equal to 3 and theta equal to half, okay, this is going to be the value. Similarly, we can find all the values, right? And for each theta, if you add all the probability, it should be 1. Okay, for each theta, row total should be 1. That you can verify. The row total should be 1. Okay, that is the property of PMF. Now, what is if you look at this problem very intuitively? Okay, working out MLE is directly it is going to take too much of time. Okay, working out MLE directly it takes too much of time in the sense that we have to find the joint density, we have to find the say where that function gets maximized and everything. Okay, but of course here it is a discrete type distribution that there again you have to go in jumps. Okay, it is not a continuous type random variable. We cannot exploit the technique of differentiation or integration, something of the sort. So we should be very careful at things. Okay, so a sample of size 1 is drawn. Okay, here we have a sample of size 1. That means we have taken only one sample from the population and it is found to be 3. So this is the most crucial information. We know that it is 3. We have that we have the value of the distribution as 3. And when we have the value of the distribution to be 3, then we should carefully check at this. Okay, so what is your MLE? MLE is nothing but maximization of your fx theta, okay, for theta. So this is the idea. This is the idea. So normally we consider for generally fx theta. So we have different ways of putting it. Okay. At times we will write something like f theta of x. This is your density. Okay. This is your density or PMF, anything. Okay. If it is discrete, PMF. If it is continuous, it is called a density. Okay, f theta of x. That means here, given theta, okay, if you know the distribution, as I said, if I know it is 1 by 4, so you can add these things and verify. Okay. Similarly, continuous case, you can integrate and see it is 1. This total is 1. This is density concept. Okay. But now, when you consider likelihood, okay, so we will take the same fx theta. We will take the same fx theta. So fx theta. But in this case, what happens is we know that x is known. We know that we assume that x is known and theta is unknown. Theta is unknown. Theta is. So when we want to maximize this, okay, for what value of theta? Okay, for what value of theta? And of course, theta should be a function of x. In general, it can be a function of x1, x2, etc., xn. Okay, here we are taking only one sample, so it should be a function of x1 alone. Okay, so I should see that for what value of theta this function gets maximized. So I should maximize with respect to theta, and that is my theta hat, or that is my MLE of theta. This is nothing but your MLE. Okay, This is nothing but your MLE of theta. Okay, now let me see how to judicially access this value from the table. Okay, so I will get the table. Okay, so now I think we can process side by side so that we can have a comparison. So as usual, I will split the board. Okay, so now we will compare. Okay, so as I said, my MLE of theta, it is denoted by theta hat, which is equal to, I have a function fx theta, okay, fx theta, and I want this to be maximized for theta, maximized for theta. In addition, I said theta should be a function of the lone sample x1. Okay, this is the only sample. My sample size is 1 in this case. Sample size is 1. Okay, which is equal to. So also we said when it is considered as a likelihood. Okay, so I will put it here. When it is density, something like fx theta. Here already we have mentioned that theta known, okay, x unknown, and when it is likelihood, so it is still fx theta, but here x is known. In this case, it is 3. It is given to be 3. You can refer here. Okay, you can refer here. It is given as 3. Okay, x is known, but theta is unknown. So theta is what we want to estimate. So now you can see when x is known, what will happen? Your theta hat is equal to maximum of f. X is now 3, or I will put x is equal to 3. That is better. X is equal to 3 theta, and I want the maximum value of theta. For what value of theta? This function is made. There is a great difference between function attaining a maximum value and at what point it attains maximum. See, they are two different things. One should be very careful. Right? Normally it is something like that, something like this. You should be very careful because it is a function of x and theta. It can be misleading at times. So that confusion only normally examiners will exploit. So it is something like this. Okay, so you have the x-axis, y-axis, and this is your this is your theta, which takes a value. Okay, for what value of this? Here we have fx theta. Okay, we have fx theta. It is something like this. So it may rise to a certain point and it may start decreasing, right? So this is the point. This is the point at which maximum is attained. And we are not interested in this value. Okay, this is the maximum f of x because it increases and it reaches the maximum here. Okay, and this is the maximum here. But we are not bothered about this maximum. This is not our MLE, right? So maximum of that's why we should be very careful. It is not. It is the value of theta at which it is maximized. So here it is this value. Here, if you carefully see, it is this value. Okay. This is my theta at which fx theta is maximized. Okay, this is this value of theta. So this is theta axis. So say this is theta 1. At theta 1, it is being maximized. At theta 1, it is being maximized. So in that context, we should be very careful. So we should maximize the function, but we are not interested in the maximum value of the function, but at what value of the argument it gets maximized. Okay, now let us see when it is given as x is equal to 3. So here we have a two-way table in which your columns varies with respect to x, 2, 3, 4, 5. You can see here. Okay, or I will make a different color. So this is your column in which x varies 2, 3, 4, 5. And this is where your theta varies differently, 1 by 4 to 1 by 2, 3 by 4. Okay. So, but here we need not consider the entire table. Okay, we need not consider the entire table because it is given that x is equal to 3. X is equal to 3 here. So that means we have to consider only this particular column. We have to consider only this particular column. And what is the maximum here? Here the maximum value is 0.4. Here the maximum value is 0.4. And be careful in the sense that, one sec, it is not working. This is the maximum value, right? But it is something like this value, the maximum value that you have here. The maximum value that you have here. But what we are interested is at what point it is getting maximum. At what point it is getting maximum. So you go through this column and this is the maximum value, and we are not interested in this maximum value, but at what theta it is going to be maximized. Okay, at what theta it is going to be maximized. That value is this. At theta equal to 1 by 2. Okay, at theta equal to 1 by 2, it gets maximized. So in that sense, so now my theta value or maximum likelihood estimator of theta, which is theta hat, is equal to, okay, I will put it there. So MLE of theta, which is equal to theta hat, which is equal to 1 by 2. So this is what the final answer is. So with the help of the table, okay, so we are supposed to find the estimator, okay, because this estimator, normally we will be replacing this estimator in the test function when we go for likelihood ratio test in the next class. That is, in a way, this is connected to the test. Though this is the estimation problem of MLE, maximum likelihood estimation, this estimator is going to be replaced in the likelihood ratio test, okay, in the numerator as well as in the denominator, that we will be possibly seeing in the next class. That is the idea. So what I suggest is, if you are careful enough, okay, so since I am explaining this from the fundamentals, okay, it naturally takes more time. Suppose if you clearly see the concepts, okay, once the concepts is there well built in your mind, then probably what remains when they are given x is equal to 3, you go to 3, consider the column. You should be very careful. At times they may transpose this table also. At times they may transpose the table. So if it is a transpose, then x values will appear in the rows and your theta value appears in the columns. Then you have to select accordingly the row. Now it is, since x is appearing in the row head, I am selecting the column. So if it is 3, select the column 3 and search for the maximum value, and don't struck at that particular value, because see the careful point here. So we have theta values ranging in between 0 and 1. 1 by 4, 0.25, this is 0.5, this is 0.75. Okay, so the probability values here also, it ranges from 0 to 1. So there is every chance immediately that we will jump into conclusion that it is 0.4, which is well within 0-1 limit. Okay, but that is not the case. You catch hold of the maximum in the row and take that value which actually leads, that value of theta which is leading to this maximum. Okay, it is that value of theta which leads to the maximum. You should not struck with the value of 0.4. That is the problem. So if you clearly observe the structure, okay, if I will put it in a different way. Suppose if the same problem is asked with x is given as 5 instead of 3, if x is given as 5, immediately what we will suggest is we will go to the column corresponding to x is equal to 5 and select what is the maximum. Okay, this is the maximum, and correspondingly this maximum is led because of theta equal to 1 by 4. So in that case my theta hat MLE is 1 by 4. That's all. So here it is, since it is 3, it is off. When it is 5, it is 1 by 4. Similarly, you can also check with what happens when x is equal to 2. When x is equal to 2, we can have the maximum value at 0.3 and the corresponding thing is 1 by 2. And the corresponding thing is 1 by 2. So here now you can see one more thing also. Whether it is 3 or 2, okay, even see when it is 3 also we are concluding this is our maximum, okay. I will put it like this. So when it is 3 also, conclusion is 1 by 2. So when it is 2, here also you can see, okay, when it is 2, of the 3, 0.3 is maximum, for which theta is off. Okay, so when we have something like x is equal to 2, okay, this also implies your MLE theta hat equal to 1 by 2. For different values of x, there is a possibility that you can get your same theta value, okay, for same theta value. So it may be asked in a different way also. Say for example, for what values of x 1 by 2 serves as a particular value, right? So here x is given and you are supposed to find out what is the MLE. Okay, so on the contrary, to make the things little bit complicated, they may ask, this is my MLE, okay, this is my MLE. So you can say that what about the possible outcome? So it is not a one-to-one. See, previously when x is given, MLE is unique. If it is 5, it is 1 by 4. If it is 3, it is 1 by 2. If it is 2, it is 1 by 2. So given x, there is only one value of MLE. Okay. On the other hand, if MLE is given, corresponding to MLE, we can find a different x's. So we can land up with 3 as in our case, which may lead to 1 by 2 as MLE. We can land up with 2, which may again lead to your MLE as 1 by 2. So we should be very careful when doing it in the other direction. Okay, doing it in the other direction, saying that x is given, find the MLE. Okay, instead of that, if MLE is given, what are all the possibilities of x? Okay, so you should be in a position to do the problem in both directions. So that is the point that I want to make. Okay, let me save this first. Sir, how much time I am left with? Excuse me. How long I can go? Yes. Hello. Hello.
Yes, sir.
Sir, how long I can go? How much more time I am left with?
Sir, already time over, sir.
Time over. Okay.
Try to finish the session, sir.
Okay. Then I will take some 2 minutes to conclude. Okay?
Sure, sir. Sure, you can take. Sir.
Okay. Yeah. See, what we are telling about the thing is that we started with the concept of testing of hypothesis, and this testing of hypothesis actually it means that we have been introducing null hypothesis and alternate hypothesis, and we said the null hypothesis is something which we want to prove or disprove. That is what that is the starting point. And alternate hypothesis is one that is that negates your null hypothesis. That is the idea of your alternative hypothesis. And then we went on defining what is type 1 error, type 2 error, rejecting the null hypothesis when it is true, it is type 1 error, and not rejecting the null hypothesis. Okay, not rejecting means it is accepting. Okay, when the other parameter structure is true, okay, that is called type 2 error. So thus we have type 1, type 2 error, which are at logarithms at each other. So as one increases, other decreases. So we said that we will give more importance to type 1 error because of its serious nature. So we will fix normally type 1 error at 0.05 or 0.01, okay, literally 5% and 1%. And we try to minimize the type 2 error. This is the thing what is mostly done in testing of hypothesis. And in case of continuous type random variable, all the probabilities of type 1 error and type 2 error and power, which is nothing but 1 minus type 2 error, they are all estimated using integrals. At times we will be integrating with respect to a single variable or simple integration, and at times we need to use two-dimensional integration or multiple integral. That is what we have seen in the first problem. And in the second problem, the same construction of the critical region, we went for a discrete type setup. That is also a testing problem in which the test critical region has a tie. So we could see that when we have something like 0 or 1, we have the same size, something like 6 by 32 if I remember correctly. And 4 and 5, again we have the same size, 6 by 32. So now there is a dilemma, which is there is a tie. So there are two critical regions having the same size, but in the problem it was asked that we are supposed to find the best critical region. Okay, so in order to, if the criteria of best critical region says that if the levels are tied or if the sizes are tied, then we have to go for what is called power of the test, and the power we have found it something like in the second region, I think the power is maximum, that is 4,5. So we decided the critical region to be 4,5. And about the last problem that was in which we were developing the MLE. So we have focused on two things. One is that how likelihood function has to be considered as a function of theta, not as a function of x, because x is known. It is given to be 3, 4 or some values. Okay. And in this problem, we have found out the value of theta for which the function is maximized. We stress the fact that we are not interested in the maximum value of the function, but the point at which it is getting maximized. So that is what we are trying to do. And we have also done it the other way. So we have changed the value of x, and we have seen if for changed value, how your MLE changes. And one more reverse transformation we have done is, so given x, we have found out MLE. And given MLE, okay, so we should also be, we set certain tips to find what are all the possible x's, okay. So I think with this, I can conclude my class. Thanks for watching. Sir, shall I pull out?
Sure, sir.
Okay, thank you. Thank you very much for your cooperation.